Okay, the isotope carbon-14 has a half-life of 5,715, roughly-ish. If you start off with 10 grams, how much do you have after 2,300? So that is just 10 times 1/2 to the 2,300 divided by 5,715. And so you just plug that in your calculator. Boom. And there you go. You get 7.566 grams. Okay, that one went pretty well. That was good. Some people made it a little bit harder than it needed to be by actually like creating an equation and moving stuff around to solve for it. Your unknown was already by itself over here, so there's no need to do algebra. Just plug it in. Part B, how many years will it take for 10 grams to decay down to 4.1? So your equation is going to be 4.1. Here, let me zoom in on this. So the equation you're going to create is 4.1 equals 10 times 1/2 to the t over 5,715. The first thing you're going to do is divide both sides by 10. So 4.1 tenths equals 1/2 to the t over 5,715. One of the things I noticed on this quiz is a lot of people start plugging into their calculators early, get decimals, and then they round. Especially when dealing with exponentials and logarithms and trig functions and these weird functions that have really rapid growth. You don't want to round early in the problem because that rounding error will get exaggerated. You might round to 3 decimal places, but by the time you take the log of it, it's only going to be accurate to like the nearest whole number, surprisingly. So I highly recommend you not round early, though, is 4.1 divided by 10 going to give you an active decimal you're going to have to round? No. So if you call that 0.41, you'll be okay. It was later on where people were rounding early and their answers weren't even accurate to the nearest tenth. So be careful. So then what I would do is take a log base 1/2 of both sides. Here, I'll take it. So you get the log base 1/2 of 0.41 equals t divided by 5,715. And then you just multiply. So you get t equals whatever 5,715 is, or times the log base 1/2 of 0.41. So 5,715 times the log base 1/2 of 0.41. And you should get 7351.228. And that would be years. Okay, and again, I said 3 places after the decimal. So 7351.228. Good? That one also went pretty well. Number 2, the population P, which is in thousands of Pittsburgh from 1990 to 2000, is given by 372.55 e to the negative 0.01052 t. According to this model, is the population increasing or decreasing over that span? Here's how I did it. I actually said this is P equals 372.55 times, and then I actually did E raised to the negative 0.01052 power. So it's 0.9895. Okay? So that's a different way you could write the model. They gave it to us as a base E exponential. You could rewrite it as a base 0.9895. The fact that that number right there is a number less than 1 tells me that this is what type of exponential growth, or growth or decay. It's exponential decay. So the answer is decreasing. Okay? So this is actually an exponential decay model because the number is smaller than 1. Just like half-life. 1/2 is less than 1. Now, what a lot of people did is they actually plugged in 1990, plugged in 2000, and it's all the numbers are getting smaller. That's great. Nobody missed that problem. Everybody got decreasing. What are the populations of Pittsburgh in 1990, 2000, 2004? Here's how I did the problem. I went to y equals, and I plugged that equation in. 372.55 e to the negative 0.01052 x power like that. But I did not use my table because my table can only show me so many decimals. So I actually went back to the home screen. And if you go to vars, yvars, functions, you can select y1, and you can plug in whatever number you want. So I'm going to say, what is y1 of 0? That's for the year 1990, and it actually gives me 372.55. So that means in 1990, the population was 372,550. What do I plug in for the year 2000? 10. So let's call this 10. So that is 335,348.824. Of which, of course, you can't have a fraction of a person, but this is a model. It's not exact. It's, you know, just meant to go. So I accepted any rounding of that clearly was correct. And then for the year 2004, we plug in 14. So 321,530.130. Okay. And as a teacher grading your work, even though the decimal is clearly unrealistic, I like to see it because that shows me even more that, one, you knew how to type this in your calculator in a way that gave you that accurate decimal, and two, that you actually did type in the right thing. On a problem like this, not such a big deal, but on some of the ones where the numbers are smaller, I want to see those correct decimals. Part C, according to the model, when will the population be approximately 300,000? Well, 300,000 people is the number 300. That was the biggest mistake. People actually wrote 300,000. And because the population is decreasing, you would have actually gotten a negative number that was like thousands of years in the past, because that is when, according to this mathematical model, the population would have been at 300 million people. Okay? But instead, it's 300, so then you got your 372.55 e to the negative 0.01052t. You divide, and a lot of people actually divided here in their calculator and got like 0.805. Is that correct? Had you done that, you would have gotten some rounding error and wouldn't have gotten the exact answer for t. Then we take a natural log of both sides, the natural log of 300 over 372.55 equals negative 0.01052t, and then you just divide. So your answer is going to be the natural log of 300 divided by 372.55, all divided by a negative 0.01052. If you type that in your calculator, you should have gotten this, which was great, and then a lot of you actually specified it as a year, which I think it would have been 2010, but I was more interested in that decimal number. $20.588. Any questions over that one? So a lot of people, because of rounding error, got 20.6. So try not to round so early in the problem. Okay, and the final problem, and again, this was corrected to be 0.1, our exponential regression. So let's get the calculator out. Stat edit, let's clear these out. So we say 0.1, 2, 4, 6, 8, 10. Is that the last data point? And then for the y coordinates, 4, whoops. There we go. 4, 6.9. Ah! 4, 6.9, 18, 32.3, 59.1, 118 point, oh golly. There we go. It's obvious to us as you look at the way those numbers are growing. Not only are the numbers growing, but the amount they're growing by is also growing, right? And the amount they're growing by is growing, and the amount they're growing by is growing, and the amount is growing by, the amount is growing. But by definition, is exponential. Like it is, we know it is, but we'll still get the correlation coefficients and see what fits better. So once you get the data plugged in, you go stat, calc, 0, L1, L2. There's your exponential regression, and here was the trick. Right? How many of you were tricked?
I wasn't tricked, but I just
Okay. So your calculator gives you y equals 3.894 times 1.412 to the x power. And that is correct, right? And that correlation coefficient is 0.997. That's amazing. But I asked for it in the form a times e to the something x. And I think another part of the reason this was tricky is I used the same letter, b, as your calculator uses here. Those aren't the same number, though, right? I should have used a different letter, maybe. Or maybe I shouldn't have. I should have left it like that. So how do I translate this so that it is of the form something times e to the something x, okay? The reality is this number here in front stays the same. That one doesn't have to change at all. Did you make it?
I think I got it.
Okay. Yeah.
Oh, sorry.
Okay. So how can I rewrite the number 1.412 so that it is a power of e? And that's the definition of what a logarithm is. If you ever have a number, any number, and you want to write it as a power of e, just take the natural log of that number. So in our calculator, we're going to say, hey, I want the natural log of this 1.412 number. That number is actually stored in my calculator, so I'm actually going to use the stored version so that I have as many accurate decimals as possible. So I'm just going to say what's the natural log of lowercase b, and you get 0.345. So your answer should have been 3.894 times e to the 0.345x. And you can check if that's correct. Take e and raise it to the 0.345, and what should you get as your answer? 1.412. Okay? So that was the trick there. Then I also want you to do a log regression. So if you go stat, calc, the natural log regression is number 9. So you can write down 23.722 plus, why are you mad? No. Yeah. So there's your natural log regression, 23.722 plus 16.211 natural log x. Its correlation coefficient was very poopy, and so clearly the exponential fits better.
Can you grade mine right now?
I just did. It's subpar.
Above 70?
I'm teasing. I didn't even look at it.